Okay, hi. In this video, we're going to be going over just a few things on implementing queues. So yeah, actually this video will probably be relatively short because I only have a few things to say about the actual implementations. I'll try to have another second video like we did for stacks where we talk about, look at kind of applying queues to some problems and things. So, but yeah, like we did before, I'll say a few words about the queue abstract data type, and then we'll look at a little bit the implementation of a queue using using an array-based implementation where you allocate some memory for your queue items, or using a linked list implementation where you allocate the memory dynamically. All right. So as before with stacks, I've got an implementation of a queue example. I'll post this code with the video. This, if I didn't mention it before, for the stacks, the kind of the implementation of the ADT for the queues and the stacks they give you in these videos they're a little bit of a combination of the Malik textbook's definition and the Schaffer's supplemental textbook that we've been using for this class. So anyway, let me just mention a few things about the queue abstraction. Okay, right? So I mean they're relatively similar, right? So they look pretty similar, a queue and a stack, and the interface, the abstraction for them. So the difference, and I hope that most people already have kind of run across this before. So the difference for the stack is a first in, last out. Okay, so the first thing that you push into the stack will go to the bottom. Or you can also call a stack a last in, first out. So the last item you push is going to be at the top of the stack, and that'll be the first thing that'll come out if you start taking things out of the stack, right? So queues are different in that they are first in, first out, right? So they're commonly referred to as FIFO structures. The first item you put into a queue is the first item that'll come out, right? So queues are probably more familiar to people, non-computer scientists, than stacks, right? So I mean, so you might stack plates and things, but you definitely deal with queues all the time in social situations. So whenever you go to a business or a restaurant or something, you might have to queue up to get service at it. So we all know kind of, and maybe dread having to queue up in line, waiting our turns for things. But queues are natural ways of organizing systems where you need to implement some kind of a fairness, right? So you need to keep track of who's been waiting the longest and then service them in the order that they arrived at whatever for service, okay? So, and probably in the next video, we'll talk more about, applications of queues. So, like stacks, queues and stacks are fundamental data types in computer science, so they're used all over, and queues are used all over as well, like stacks, so lots of things. So whenever we're building systems where you've got packets coming in from the internet and you need to handle the packets in the order they arrive, you have to use queues. Or whenever you are building an operating system, and you've got processes running on your operating system, and you need to keep track of which processes have been waiting the longest. If you've only got like one CPU on your system, you want to have some sort of ordering on when you schedule the processes. So the process that's been waiting the longest might be the next one you schedule, and then the second longest comes after that, and so on, right? So anyway, queues are used all over in computer science, and actually queuing theory is an important part of theoretical computer science in different areas. So in things like building operating systems and comparing algorithms for networking and algorithms for cryptography, queuing theory comes in a lot in different areas of theoretical computer science. So. All right, anyway, let's move on. So let's just look at the abstraction or the interface for a queue, right? So like I said, there's a lot of similarities. So Most of these method names, again, I kind of preferred the abstractions, at least the names for these methods from the Schaffer book, you know. So clear is what our Malik textbook called the what was it, the delete queue, I think. So like instead of delete stack and delete queue, we might call it clear. So that's the method for just emptying out. So putting your queue, in this case, back to an empty state with no items in the queue. Is empty, so there's a couple of accessor methods. So is empty to query whether the queue currently is empty or not, has any items waiting on it. And length, so we might want to know how many people or how many items are currently waiting on our queue. And then the actual heart of the methods, and again, the Malik textbook called these things like I'm forgetting now, but I think it was like add item and remove item, which I don't like so much. So it's more typical. The names in the Schaffer textbook for our queue abstraction are more typical of the names for our abstract data type, or abstract queue data type. So you might have an in-queue method to add a new item to the end of your queue, and you might have a dequeue method. So that whatever item is at the front of the queue, the dequeue method will take that item off. But like for our stack, typically we define two methods. So if you want to remove the item from the front of the queue and do something with it, you first have to use front to look at the front item, or to get a reference to the front item, the item at the front of the queue. And then once you're done processing the front item, you'll typically dequeue it. Okay. Some abstractions combine these two into one method. So you might have like a front and dequeue method that returns the front item and then removes it from the front of the queue. Okay. But a lot of the abstractions define this as two separate methods, and so that's how we do that in our example. And both of our textbooks, definitions of the abstract queue data type define it as two methods. Okay. And also in both of our textbooks are required in our supplemental textbook, they present the implementation of the queue as using inheritance, so using an abstract base class. So I've done the same thing. We did the same thing for the stack, and we basically do the same thing for the queue for both of these. So, and we also templatize these. So since we're implementing these in C, we use a template class so that we can have a queue of any type of item. So we can have a queue of strings or a queue of floats or whatever we want, right? So yeah, I mean our base class called queue, both for this and I think it was called queue type in the Malik textbook, right? But just defines these are just pure virtual functions. There's no implementation for these. So if you want to make a concrete implementation, you have to implement these functions. You have to implement this interface, okay? And like before, you know, you can implement a queue in various ways. So the most common way is a concrete implementation that uses an array. So you allocate memory in a block of memory to hold your queue items, right? And you can also implement it as a linked list. And I have examples of both of these. So further on in this queue.hpp function, you'll see a linked list implementation called LQ for the linked list one, right? But yeah, let me go back. Let me just mention a few things about the array implementation. All right. So again, my implementation isn't exactly like the example from our Malik textbook. Okay. So the easiest thing you can do using an array implementation is just to have a fixed sized queue. So you give an initial allocation size, and then your queue can't hold any more than that number of items, right? So if you do that, if you use a statically allocated array, which is what our Malik textbook does, and you'd have and maybe you can create your queue of a specific size when you initialize it, but after that it can't grow. Okay, so that's just a drawback. That's just a fixed size queue. That if your queue gets full, then you do have to detect that. You want to be careful that if your queue gets full, that you don't allow any more items to be pushed onto the queue until something's done with that. Okay, so but if you do that, in my implementation here, actually dynamically grows the queue. Okay, so I did the same thing as we did for the stack. So instead of setting that to a fixed size which defaults to it only allowing 100 items on the queue, I have an implementation here that you ought to look through that will detect if the queue becomes full, and instead of just giving an error message, a full queue error message, will dynamically resize the queue to double the size, basically. So actually that works fine. I'll show that here in a second. And there's not too much you have to do in order to do that, both for the stack and the queue. You just have to be careful in the in-queue method to check first that the stack or the queue is full. And if it is, you first go into the trouble of doubling the size, and then for both of those implementations, you have to copy over all the values from the old array to the new array. But then once you do that, then you can just carry on after you've doubled your size of the array. Okay? But the actual issue that I wanted to talk about for the array-based implementation for the queue is both of our textbooks talk about this. There's this conceptual problem with our array-based implementation for a queue. So the idea is if we add items on to the end of the array, so let's say we set our front of the queue to be at index 0, and then whenever we in-queue a new item, we just add it to the next higher index in the array. So the first item gets in-queued at index 0, but the next item would be in-queued at index 1, and then index 2, and then so on, right? So that's fine. That ends up being that your in-queue, you're adding items to the end of the array, is order 1 or constant time. You just keep an index to the, you just keep track of what the back index is, and then whenever you need to in-queue an item, you just stick it there and you increment your back index by 1, right? But if you do that, and then eventually, your queue would get full. But if your front item, if in the meantime, if you've removed some of the front items, so your front item, so your DQ could also be order 1, because you can also keep track of which is the front item. So if you want to DQ or remove an item, if front index is pointing to 0, you just remove that item and then just increment front index as well. So now the front of your queue is item 1, okay? So the problem, though, is that even though, like, if my queue is size 100, so if I'm using a fixed size queue and I don't grow it, you would actually have less than 100 items once you start dequeuing items from there. So you don't want to do that. So one way you can handle that is you can shift items, okay? So you can, anytime you dequeue an item, instead of just incrementing your front index to the next item, you could instead move the item from index 1 down to index 0, and then from 2 to 1, and so on, okay? So that's known as shifting the items. But that has the big drawbacks that now, if you're doing that for the DQ, your DQ is no longer order 1. It's no longer constant time. So every time you remove an item, you have to shift all in items down in the array. So now your DQ becomes an order in operation instead of an order 1 operation, right? So instead of constant time, it becomes linear time. And you can imagine, like, if you have queues with hundreds of thousands or millions of items, all of a sudden it starts taking time to do all that shifting, right? And you kind of want to avoid that. And you can't avoid it the other way. So instead of shifting when you DQ, you could always add items at index 0. So make the front of the queue the larger index. Okay, so that whenever you're in queuing an item, you're going to be always putting it at index 0. But to do that, then when you're in queuing becomes order in that case, right? Because if I want to add my item at index 0, if I have any other items, I have to shift all those other items up 1 index now instead of down 1 index in order to place that new item at index 0. Okay, so neither of those is solutions. So whichever way you do that, if you have shifting, either your in queue or your DQ becomes an order in, a linear time operation, all right? So what is normally done when you have an array-based solution is instead you treat your array as a circular buffer, okay? And both of our textbooks, our required textbook and the supplemental textbook, that's what they do for the array-based implementation. So we treat the items, the array of items, as a circular buffer. So then, if and in this case, what we're going to be doing is the front item is going to be growing. So initially, the front index points to index 0. I'm sorry, because we're pushing items onto the back. So the back index actually grows, and the front index kind of. So initially, the front index will be pointing at 0, and as will the back index. But when we push items, when we in-queue items, so initially the first item will go at index 0, and then if we add another item, it'll go at index 1. So back index will be 1, and then if we add another item, the back index will be 2. Okay, so back index will be a larger index than the front index, except if our current size of the array is 100. If we go past the end of that array, we'll wrap around, okay? And as long as we have less than whatever our allocation size is of items, we'll be treating this array of items as a circular buffer, okay? Only if our array becomes truly full, if the number of items is equal to the allocation size, and we're trying to in-queue one more items and it can't fit, will this implementation that I show you will actually grow the size. But if that's not true, if we're trying to add items and our number of items is less than the allocation size, we're going to be treating our items buffer, our items array, as a circular buffer then. Okay. So so now it's beginning to be a bit complex. There's a lot of details that we have to keep track of. In order to do this correctly, we have to keep track of all these. So not only do we have an array of items which is dynamically allocated, and it can be dynamically reallocated if we need to grow the array, but we have to keep track of all of these. The current size of our allocation, so the number of items, the current size of our array, and then the current number of items that are actually on the queue. And the number of items has to be less than or equal to the allocation size. Okay, so if I currently have enough room to hold 100 items, the number of items has to be 100 or less. Right? As soon as it becomes 100, and I try to in-queue the 101st item, in this implementation, we have to grow the array, so we have to double the allocation size. Okay. And then we also, in order to treat the array as a circular buffer, we have to keep track of the front and the back index, and we have to wrap those around. Okay, so if we're pushing items on the back and we push them past the end of the array, it needs to wrap around back to index 0 and then start pushing from there until it becomes full, in which case we need to expand the size of the number of items that we have allocated. All right. So anyway, to implement our concrete array-based queue, we just have to implement all those methods. Okay. So you can look at these. Most of these methods aren't too complicated if you understand what's going on. So I'll skip over kind of the constructor and the destructor. So the destructor all it needs to do is dynamically deallocate or free up the memory that we currently have allocated. The constructor, we just have to make certain we initialize everything correctly. One thing I should point out is notice that the back index is initialized to the end, the last index in the array. So if we allocate enough room to hold 100 items, back index is going to be pointing to index 99, and I'll show why here in a second. So initially front index points to 0 and back index points to 99 for an allocation size of 100. So is empty, I mean, there's a couple of ways you could implement is empty. You could check whether front and back index are basically equal, or actually, so notice empty is indicated by front being 0 and back being 99. So you have to check if I add 1 to back index and it's equal to front index, that's the indication that it's empty. Or it's simpler just to use number of items. So if number of items is 0, and we use the simplest here, that's an indication that the queue is currently empty. Likewise for full. Actually, is full probably wouldn't be used in this implementation since the queue grows dynamically. A user of the queue doesn't have to worry if it's full or not. Okay, so I should probably make this method private. It's just used internally in the queue to check if we really are full. So if the number of items is equal to the current allocation size, we have to grow our array-based implementation, right? All right, so let's look at in queue and dequeue and front. So those will be the ones that are that will take that will be our more complex methods. And those are the ones that actually do things with our queue. Right? So if the queue isn't full, it's not too tough. So the basic the basic thing you're doing for an array-based implementation for a queue is the back index points to the location where you want to insert the next item, the new item that you're in queuing here. Actually, so what we're doing is the back index points to the one before the next item. So it points to the actual back item. So it points to the index containing the actual back item if the queue isn't empty, all right? So initially, back index points to 99 if we allocated 100 items. So what we do is we increment it by 1. So we add 1 to that because we don't want to overwrite what the back item is pointing to. We want it to increment it. But we also treat the buffer as a circular buffer. So the array is a circular array here. So after we increment by 1, we do a mod by the alloc size. Okay, so that if we went past the end of our buffer, we will wrap back around to 0. Okay, so again, when back index is 99, we'll add 1 to it. That'll be 100. And then when you do a mod by 100, this will actually wrap it back around to 0. Okay, so that's how when the array is empty, when we in-queue our first item, this wraps it back around to 0. We set the number of items to go from 0 to 1 when we increment. and then we insert the item, the new item at index 0, basically, right? So make certain you understand that. So notice, after we inserted the first item, back index is 0. So the way you should think about it is back index always is pointing to the actual index where the last item is, and front index is always pointing to the actual index in the array where the front item is. Okay, so after I've inserted one item and only have one item in the array, both front and back, that one item is both at the front and the back of the queue. Okay, so both front index is going to be 0 after inserting the first item, and back index is going to be 0 after inserting the first item. Okay, so imagine that I've inserted one item and front index and back index are both 0. So think about what happens when you insert the second item, right? So when you come in here, if you go down here, so again back index is 1, so we just add 1 to it. And modding by like 100 is not going to do anything. So the back index is still going to be 1 in that case. So in that case, yeah, we're just going to end up putting the new item, the second item, at index 1. All right. So if you don't follow that, you should think about that and make certain that you understand how that works. That we get our new item into the array. So our second and third and so on items. And I skipped over those. So if the array is full, then what we do is we just allocate, we double the size of the array. So again, remember, is full is only true, if we have an allocation size of 100 and there's exactly 100 items in there, then we can't actually add one more item in there. It would overwrite an existing item. So we allocate a new array that's double the size, and then here we kind of trickily, like we did for the stack, we have to copy the items from the old array to our new array, so from items to new items. And what I did in this implementation, no matter wherever front was pointing, I just copied the front item from the old front index to index 0. Okay, so we start at front index wherever it is in the old array, and it just gets moved to index 0. And then the second item gets moved to index 1, and so on. So we end up then, after we double the size of the array, with the front item at index 0 and the back item at index number of items minus 1. All right. So that's the cleanest thing to do. Since you have to copy the items anyway, you might as well copy them back to index 0. So, but after that, then we're then going to be treating the array as a circular buffer. So front index can move after that to not be pointing to 0. And then so by far I think the in queue is the most complicated, since you have to handle the array becoming full and changing the size of the array, so allocating some new memory. So front is like we did with the stack. If the queue is not empty, then front index is just pointing to the actual item that's at the front, so we just return that item. But if it is empty, we detect that and we throw an exception instead in this example implementation I gave you. And then dequeue, again, the dequeue, front and dequeue, the front index should always be pointing to the index in the array where the front item is. So if I want to remove that front item, I just need to increment the front index by 1, and the number of items is reduced by 1. But again, so notice we've got that %alloc size here. So again, after I increment the front index by 1 in order to remove that front item and look at the next item to be the front item, if I've gone past the end of my current array allocation, then I need to wrap around back to 0. Okay, So one way you can do that is by modding by allocation size. You could do this, so another way that some people find more understandable, instead of modding by the alloc size, is to just do an explicit check. So if so you could do it like that instead. That should be equivalent, but yeah, most implementations you'll see will use this mod here, right? So, but this basically says that, but yeah, so if front index is equal to 100, if our current allocation size is 100, that means that that's not a valid index anymore. The only valid indexes in an array of size 100 are from 0 to 99, since we use zero-based indexing. So if we incremented it and we're at 100, we have to wrap back around to 0, basically, right? So these are equivalent. That's just doing it using this mod instead of using an explicit if statement. All right. All right, so yeah, that's, I mean, and so that's basically it for our queue. We looked at the in queue and the front and the DQ. Well, I guess I didn't look at the DQ. So the DQ then, I'm just realizing there might be a bug here, so I forgot to change the front index here. I'm not certain how I didn't catch that in my debugging. So yeah, the number of items should be reduced, but but like we did for in-queuing, we have to change the front index in this case for DQ, because we're removing the front item. So it should be the same thing. Something like that. So we'll check that out there. So all right. So that's our DQ, and then there's and like before, I have some examples then of some overloaded methods in order to output the queue to a to an output stream, so we can display it. So. All right, let's see if that still builds here, and let's try running it. So. Let's see here. Let's see if it builds again. Oops. Spelled front index there. Okay, that build. Yeah, actually, I'm really not certain how that was working when I tried it out before. So let's try it here, and yeah, let's pay special attention to the DQ method here. See how it's doing here. So I'll stop it here. So yeah, in this case, kind of like we did. So remember, our queue. Our array-based queue in this case is a template class, so we can have a queue of whatever types we want. So So here we'll create a queue of strings, and we'll in-queue some items, and we'll test out some of our other things like the isEmpty, and the length before we try and dequeue some items. So yeah, after I dequeue these two items, so we can show it. So when we create our initially empty queue, and we display, and we ask if it's empty, we get that it's true that it's empty. And if we display it, we see that there's nothing on it. So I display things from front to back, from left to right, if you look at the toString method here. Then we enqueue 3 items, and we look at our queue. So now we see that yeah. So notice that Derek went on first, so it should be at the front, followed by Susan, followed by Alan is at the end of our queue. So that should be at the back of the queue. So our front item is Derek, followed by Susan, followed by Alan at the back. Right. So now our queue is no longer empty, and the length of the queue is 3 because there's 3 items on there. And after we remove 2 items, so Derek and Susan should have come off, and then we only got 1 item left on the queue, and so Alan should be at the front there, basically, all right? So yeah, that's working now. Then yeah, so we can try our other things. So see what happens if we try and look at front or try and dequeue from an empty queue, make certain that we're throwing our exception. So yeah, indeed, after we dequeue our last item, the queue is empty again, and if we ask for front, an exception will actually occur if you look at the implementation this implementation I gave, or if you try and dequeue from an empty queue, you'll get a empty queue exception as well. So yeah, and then kind of here, just a real quick check that in this case that the queue is actually growing. You know, so if we add 120 items to our queue, which only has enough memory allocated to hold 100, it shouldn't crash or anything. So it should actually in-queue these items, and we should be able to see all 120 items if we push them on there. Because once it gets to 100, it'll double the size of the queue to 200. So yeah, if we display those items, yeah, we get those 120 items on there. So, all right. So yeah, that hopefully that should be working. So let's then kind of look at the other, see if there's anything to add about the implementation for a linked list version of our queue, right? So. The linked list version is in some ways decidedly easier because you don't have to worry about growing it, nor do you have to worry about treating the buffer as a circular buffer. Both of those make the array-based implementation kind of complex. So if you're comfortable with using pointers and linked list, the array-based implementation it doesn't have any of those limitations, so it won't get full unless you fill up your computer's memory, of course. And it's relatively easier to implement the in-queue and the dequeue items, right? So here for a linked list based implementation, we just want to keep a pointer to the front and the back of the linked list. And for convenience, in order to implement a linked method, we also will keep track of the number of items, so that we don't have to use an order in operation to count them up. So we'll just keep the number of items up to date, so we can return the length accessor method. So for a linked list implementation, if both front and back are pointing to null, that's an indication that the list is empty. And if we delete the queue or if we explicitly call the clear method, that's the the Malik textbook called that delete queue, I think, or empty queue. So again, you have to be careful that you manage your memory correctly. So if you want to actually clear out or empty the queue, you need to iterate through all the items and send delete messages to every one of your nodes to free up or deallocate all your memory. So, all right, so let's just look at enqueue and dequeue and front. Okay, so front will be trivial, right? So we've got a pointer to our front item. So as long as the queue isn't empty, we just return that item. Otherwise, we throw our exception in this implementation. And enqueue is relatively straightforward if you're comfortable with working with linked lists. So we just allocate a new node of memory to hold the new item that we're adding. If the queue is empty, then this new node becomes our new front node. Okay, so if queue front is null, that means the queue is empty. So now queue front just points to the new node. If it's not empty, then queue back. We're going to add it to the back of the queue, right? So whatever the current back of the queue is, it should link now to the new node that's going to be the new back of the queue. And then whichever was the case, whether the queue is empty or not, our back item, the pointer to the back item should now be pointing to this new node. So we just point queue back to the new node. So that's it then for the enqueue. Likewise for dequeue, we want to remove the item from the front of the queue. So we just pull the front item off and send it a delete message to safely deallocate its memory. So be good managers of memory. And then once we do that, our front becomes whatever front was pointing to. Okay, so to remove our front item, you just follow the link to that front is pointing to, and make that the new front. All right, being careful that if our queue became empty, this won't automatically update queue back to also be null as well. So if the queue is empty, we want both queue front and queue back to be pointing to null. So if we follow that and queue front becomes null, that means the queue is empty. So queue back should also be set to null as well, right? And we update the number of items. All right. So I won't step through kind of our linked list version of the queue. So once you create your linked list version of the queue, so in this case I show creating a queue of doubles, so using the templatization from C++, so to have a queue of doubles instead of a queue of strings. But after that, we'll use it exactly the same way, whether we have the array-based implementation or the linked list-based implementation. So we can enqueue items, we can look at the front, we can dequeue items, and so on. All right, so yeah, that was our array and linked list-based implementations. So hopefully, you should look through kind of the example implementations I gave you. The main point, especially for the array-based implementation, I combined two kinds of relatively complex things for the array-based implementation. So we're both using treating the array as a circular buffer so that we avoid having an ON, a linear time operation when we either dequeue or enqueue an item. So the only way you can keep one of those operations from being linear time instead of constant time is to treat the array as a circular array. Okay, but then the other thing in this implementation, we show it dynamically growing so that the queue doesn't actually become full. If the queue becomes full, we do an ON operation to double the size of the array, and then the ON operation is we have to copy all the items from the old array to the new array, right? But so In that case, in queue is normally O1, but in the worst case, it can be an O in. It can be a linear time operation if we have to grow the array, double its size, and then copy all the existing items. Right? So then the linked list implementation, both the in queue and the DQ are O1. They're both constant time. It doesn't take any time to add or remove an item to in queue or DQ an item from the front or the back. Right. All right, so that's it for our queues, the implementation. I'll try and have another video where we show some examples of how you use queues to do some things with them. So some applications of queues. But that's it for arrays. Hopefully that video was helpful, and I will see you guys in the next video.